Geoscience Australia had mapped those, but not really tried to unravel this earlier and older complexity. Stefan Student has had a crack at doing this, and they've come up with something quite different. I applaud that work, and they've even inferred some steep structures here, which is good to see. If we look at that map and look at the isotopic data, the colours are the model ages of the isotopes of those intrusive rocks, and anything that's green or yellow or orange or red is increasingly, basically Archean, older Archean. Anything that's blue has a model age that's younger than Archean. Okay, and so what you find is the oldest material preserved is over here, and then as you progress westwards, you're seeing the colours gradually changing, and a bit more sort of green, yellow, orange, and with a bit of red. But then as you go further west, you're starting to get a blue, a bit more blue. So in other words, as you go west, you're getting younger model ages. Now that would be the sort of result you got if you diluted the crust. If you had Archean crust and you diluted it with a rift zone and added a lot of Proterozoic melt to the crust, that would give you this sort of net result. And in fact, that would make sense because we've got these curvilinear faults, which are highly suggestive of westward dipping, eastward divergent thrusts. They would be due to the inversion of a rift that would be located further west, where the juvenile results are. And if we look at the metamorphic gradients, we find that the lowest grade metamorphic rocks are in the east over here, and then successively higher up to amphibolite to granulite facies in this block here, and also high to the west. So that confirms basically west over east thrusting. In other words, you're inverting some sort of former Proterozoic rift here. And that inversion is part of the Kimben orogeny between 1.73 and 1.71. So it's this scenario, and it's not a case where we've had subduction. There's just been a failed rift here, but enough of a rift that there's been a lot of magmatism coming up here, and then these two blocks have come back together again, and the crust is imbricated and thrust as per the plan view there. The MT is quite spectacular. So this is the MT that's coincident with that seismic line. And you can see here that in the west, where I would nominate a rift, or the inverted rift, you've got a steep conductor, and then you've got a series of shallow, like a décollement with a series of structures coming off it. And you can see the cartoon that they've derived down at the bottom here with a detachment or décollement, and then a series of thrust structures like so. And that would be the sort of structure that you would get from inverting a rift that was focused over here on the left-hand margin. So if you take that result, so these black lines are the lines from interpreting the MT, and if you take those back and superimpose them on the seismic reflection, you can start to make some better decisions about what you would pull out of that seismic reflection line. And indeed, in the bottom diagram here, I would say we've got at least 3 sets of structures here. We've got these small black lines are probably would seem to be the oldest structures, either late Archean or early Paleoproterozoic. And then we have this second set of structures, the Kimben orogeny inversion, and then we have these green structures, which are a later Neoproterozoic orogenic event. So let's move now to the age of the lithosphere. Earlier I said that most of the lithospheric mantle is of Archean age. And so let's talk a bit more about that. First of all, let's consider the crust. So there are quite a lot of studies, particularly in the last 12 years or so, that have looked at the growth of the continental crust using isotopic data. And there are absolutely massive data sets available now using things like uranium lead with hafnium isotopes or neodymium isotopes and oxygen isotopes. And there's these studies are settling on a number that's roughly around 60%. So in other words, about 60% of today's crust is actually Archean material. That's what this data is telling us. That's plus or minus 10% from there, at least. And so you're looking at a really large amount of Archean material. Now, it's not all Archean crust. Some of it would be Archean crust, but a lot of it is just reworked and reconstituted Archean material that is now in younger sediments and younger metamorphic rocks and younger igneous rocks as well. But how would we keep 60% of the continental crust as Archean material? You can't do that unless you actually have something underneath that is protecting it from being subducted and destroyed. So it's telling you that at least 60%, in fact, more than 60% of the underlying continental mantle must be Archean originally. And you would have Archean crust under your, obviously in your known Archean terrains, some Archean lower crust in other terrains, but also many terrains might just have reworked components of Archean material. And that's what the isotopic data is telling us. So how do we recognize this? How do we actually map block by block the age of these things? So we use the crustal history as a proxy for the age of the underlying mantle roots, because without the mantle root protecting the overlying continental crust, the continental crust would not exist. So the minimum age of the maximum age of the overlying crust is the minimum age of the root underneath. We can also occasionally date the mantle roots directly from mantle xenoliths if the xenoliths are good enough using isotopes. And we can infer the age using velocity data, which we've benchmarked. So we'll talk a bit about that shortly. So in more detail, a list of some of the criteria we would use. Obviously, if you've got Archean crustal rocks, then you've got Archean mantle underneath. But also, if you've got Archean rhenium osmium isotope model ages on continental mantle xenoliths, then that's also proof of an Archean root. Archean model ages in lutetium hafnium isotopes on zircons from non-paraluminous, dominantly I-type granitoids would indicate that it's Archean basement. Similarly, with samarium neodymium isotopes on the same sorts of intrusions. Euhedral Archean inherited zircons are indicative of an Archean basement. And exclusively Archean unimodal inherited zircon populations are a strong indicator as well that you've got an old Archean basement. With medium confidence, we use the seismic velocity. Now, we've done a lot of benchmarking on Steve Grant's global data set at a depth of 100 to 175 kilometres in that layer. And that benchmarking, some of that's been published in Dean et al. 2005. There's also been thermodynamic modelling. And what we find is that the higher velocity areas in this data are only explicable by highly depleted compositions. So in other words, very iron poor lithospheric mantle. And every time that we've dated that mantle from mantle xenoliths, it's always Archean, and in fact, generally more than 3 billion years old. So the Highvelocity is a very good proxy. We would also use exclusively Archean inherited zircons where there's multiple populations as a reasonable indicator of probable Archean basement. And if you've got model ages, isotopic model ages from these isotopic systems, from I-type granitoids, in regions where there is actually no crustal event of that age, there are only younger events, then you know that it's a case of mixing younger magmas with an Archean basement will give you that younger model age. As an example, if we looked at Western China, this is the Jungle Basin, and it's a relatively flat area surrounded by mountain ranges, and it's part of the Tian Shan orogenic belt, the Central Asian orogenic belt. And this is covered, this flat basin is covered with Mesozoic and Cenozoic sediments. And for many years various publications said this was Oceanic lithosphere. However, geophysical work across this seismic lines have indicated that it's thick continental crust. And in fact, it's a continuation. And in the magnetics, you can see it's a continuation of the same Central Asian orogenic belt arcs that are present in the exposed areas. Interestingly, there are a number of areas where there's significant amount of Archean material popping up. For instance, over here, there's actually an enclave of 2.5 GA diorite gneiss coming up in a Paleozoic granitoid. So there must be Archean basement here. And over here, there are two drill holes that go through the cover sequence, the Mesozoic cover sequence, and into the Paleozoic arc rocks. And these researchers, Wang et al., found that there were inherited zircon populations in these carboniferous arc rocks, but those populations were exclusively Archean. So a late Archean and an early Archean population. Not only that, but quite a few of them, the zircons, were euhedral to subhedral in shape. So again, this is extremely strong evidence of an Archean basement. Wu et al. Then looked at the entire region and all of the zircons around this basin and put that together on an epsilon hafnium versus uranium lead age diagram. And what they found is there's a lot of Proterozoic zircons, which their model age will, if you intersect this mantle evolution line here, that will give you an Archean age of the crust that's been melted to form those zircons. But also, if you look at the Paleozoic zircons associated with the Central Asian orogenic belt, they have a very a huge range of values in epsilon hafnium, and that's the sort of range that you get when you mix a juvenile mantle melt with an Archean basement. So what we would contend is that this is in fact an Archean microcontinent, and that's the reason why the deformation and the mountain belts are partitioned around this relatively flat body. Another example, if we went to the Northern Atlantic and looked at the Arctic shelf, this is the island of Svalbard, and on Svalbard there are some Proterozoic rocks in pink, and there's Paleozoic rocks in green, and then there's some young volcanics. Those volcanics are bringing up xenoliths of lower crust, as well as xenoliths of the continental mantle. The lower crustal xenoliths are meso or paleo to meso-Archean, and they also those zircons in that material show lots of overprinting by younger events. In other words, this lithosphere has had a significant number of tectonothermal events affecting it. When you look at the mantle xenoliths, you also get an age of 3.3 billion years, and again with multiple melting overprints. So this confirms that this is Archean lithosphere, but it's multiply reworked. When you look at the seismic velocity at a depth of roughly 130, 140 kilometers, what you find is you've got the high velocity to the south where the Archean cratons are in Baltica. You've got the low velocity of the mid-Atlantic ridge here. And then you've got this medium velocity of the Arctic shelf. And that's the sort of response that you get when you've had a lot of arc magmatism pumped through the lithosphere here, and it's interacting with the continental mantle and changing its composition. And that affects the velocity and lowers it. Let's look at the southeastern US. These are a series of Proterozoic terrains stepping southeastwards as they get younger. So we've got the cratons, Archean cratons to the north, the Superior and the Wyoming. And then this is a basement map, and then shows the arc terrains of the Yavapai province, then the slightly younger arc terrains of the Mazatzal province. And again, they're younger for the granite rhyolite province, and then the Grenville down here. So the prevailing story in literature is that this is the growth of North America through the addition of fresh, juvenile, new lithosphere in a succession of growth waves. However, we would dispute this. Before we zoom in, I just want to point out that the green feature shown here is a Neoproterozoic failed rift and a locogen. That's the Oklahoma locogen and Reelfoot rift. They formed when the Rodinia supercontinent broke up and South America moved away from North America, and this failed rift was formed. It was then inverted and deformed during the Permian when South America came northwards and collided with North America during the peak of the Pangea supercontinent, and that created what is called the Washita orogeny, which inverts and deforms these basins. So let's zoom into Texas and look at the magnetics. Here's the Oklahoma locogen, quite a distinctive feature in the magnetics, quite a strong linear feature, and then it joins up with the Arkuma Basin and the Reelfoot Rift as you go further east. But interestingly, you can also see a series of broadly north-south structures, big discontinuities in the magnetics, clearly very large structures. And in the fabric here, whilst we're going north-south here, we see that as we come around here, the fabric starts to turn and becomes east-west, and then it turns and becomes northwest. That is an orogenic fabric associated with this Permian, early Permian Washita orogeny. And that's telling us that this block must be behaving as a microcontinental block with deformation partitioning along its edges. If we look at the gravity data, we get the same pattern. You've got a very isostatic residual anomaly here, dense material giving us this red color, and that's associated with a series of Neoproterozoic intrusions that were injected into that failed rift. If we look at a regional seismic velocity at a depth of 100 to 175 kilometers, we've got a small remnant of fastish velocity surrounded by lower velocity, and particularly up through the Oklahoma locogen and over to the Reelfoot Rift, slightly lower velocity, but quite distinctly high under here and very high to the north. And those signatures do look significantly like an Archean signature from our other global work. Interestingly, there is a series of lamproite intrusions. They're late Cretaceous, and this pipe in Arkansas is diamondiferous, and it's an operating diamond mine. So that's telling us that the lithosphere was thick enough and cold enough to preserve diamonds in the late Cretaceous here in this part of southern US. And generally, we find that that is usually Archean lithosphere elsewhere in the world. We were fortunate that there are mantle xenoliths here that had multiple populations of mantle sulfides in them. These were examined petrographically, and the individual pulses of mantle sulfide were analysed by in situ rhenium osmium isotopes, and that resulted in a series of ages. So here's the model ages from the mantle sulfides, and the oldest ages are Archean, between 2.5 and 3.4. And then there's a second peak here that's around 2 to 2.2 GA. And then a third peak is in the Mesoproterozoic here. And that would be the age of the granite rhyolite province, which is the dominant crust through here. It's an arc, it's a Proterozoic arc. So magmas that have fed that arc have deposited mantle sulfides in the structures beneath the arc. And then we've got a peak of Grenvillian aged mantle sulfides, and then finally a small peak of Permian aged mantle sulfides, which would match the age of the Washita orogeny. So these ages here fit perfectly the known ages of the major events in this region. So these are Laurentian events. They belong to North America, those three here. However, these older two events don't belong in North America, and they're quite possibly West African, but it's indicating this whole lithospheric belt through here is a fragment from another continent. It's a microcontinental ribbon. And the suture zone that has stitched that ribbon to North America at 1.65 is what was reactivated by those Neoproterozoic rifts. And that suture zone, that collision, was what caused the Mazatzal orogeny at about 1.65 GA. So what we would say is that North America actually grew by the addition of microcontinents, and it was subduction and rifting and lots of arc activity that enabled these ribbons to migrate across oceans and collide with North America. So what we're finding is that under our Archean terrains, we've got a lot of this old depleted iron poor, well-preserved old residue from these early plume melts. But under our Proterozoic terrains, because of the overprinting, we preserve less and less of this old depleted material. And the main agent of change is magmatism and fluids associated with subduction. If we look at mantle xenoliths, calcium versus aluminium, these are xenoliths from under Archean terrains down the bottom here, and they're very depleted. And they're also very low in iron. Whereas under our Proterozoic terrains, we have a slightly more fertile composition, higher in calcium and aluminium, and also higher in iron. And then as you come to the Phanerozoic terrains, they're even higher in calcium, aluminium, and iron. And then you get to the convecting mantle. This is the upper mantle composition, which is very fertile. So what we're observing here is the effect of refertilisation. Arc magmas are melting this convecting upper mantle, and those melts are being passed through these old roots on their way to the overlying crustal arc. And that process of feeding these melts through these depleted roots gradually changes their bulk composition. That's the process of refertilisation. We have dated all these mantle xenoliths. These are all Archean, and we are now finding that some of these guys up here are Archean. So what we're seeing here is the effect of the arc melts gradually refertilising these old roots. And the more activity you have, the more refertilised the roots become. That has the effect of lowering the seismic velocity of this mantle and increasing its density, because you're adding iron-rich rocks. And I should have pointed out that phosphoritic olivine, which is the magnesium-rich end member, which is prevalent in these old depleted roots, has its acoustic properties are such that it has a higher velocity compared to the iron-rich end member of the olivine family, which is phayolite. So as you refertilise and convert more and more of the forsterite to phayolite, to this iron-rich olivine, the seismic waves will be slower. So if we look at that diagram again, orogenic cycles in this direction, the effect of that refertilisation process means that you take this depleted material, it may have a little bit of orthoproxene, but it's mostly olivine and very magnesium-rich olivine. And then you start adding in these fertile melts, and that will begin to grow things like clinoproxene and garnet, and eventually even, as you continue on, things like phlogopite, etc. The effect of that refertilisation on the olivines is that the Mg number, which starts off as very high, gradually declines. That has also an effect on the velocity. So these roots will have slower velocity compared to these well-preserved old roots here. And the density. So this material down here will be lower density compared to this material up here. So this really becomes important during tectonic processes, because this material here is very difficult to destroy, whereas this material up here, because of its density, is relatively easily recycled, either via subduction or delamination. So if we looked at our cartoon cross-section and we put some of these densities calculated thermodynamically, we would see 3.3 grams per cubic centimetres in the depleted Archean root here. But as you refertilise it under these proterozoic terrains, that is going to increase, that density is going to increase, but it's still buoyant relative to the asthenosphere. However, oceanic plate, when it's warm, when it's first formed at a mid-ocean ridge, it's relatively iron-rich lithosphere. But because it's warm, it's relatively buoyant compared to the asthenosphere at first. But when it moves away from the ridge and cools down, it can become extremely negatively buoyant. These are very high densities. And that's why subduction occurs. And that's why there is no oceanic plate older than about 180 million years in the history of planet Earth. No oceanic plate is capable of surviving very long, simply because it becomes too dense. If we look at the relationship to gravity now, this is a traverse across the Siberian craton, roughly 500 or 600 kilometres. There are many kimberlites along this traverse, so we can sample the mantle xenoliths and get a pretty good feel for the composition of the mantle under here, and we can compare it to the gravity signature. And you can see in the Begg map shown that the density in the gravity data is higher to the northeast compared to the southwest. If we look at a cross-section of the composition of the lithosphere here from southwest to northeast, under here we've got a big thickness of very depleted compositions. So in other words, very magnesium-rich compositions. And over the top of that area, the gravity profile is about minus 30 milligauss. So you can see it's a really long wavelength negative Bouguer feature. Whereas when you cross over some major structures and into this more fertile zone of continental mantle, you'll see that this more iron-rich mantle is expressed in the gravity as a much denser feature. A quick snapshot of what a bit of the mantle looks like. This has been exhumed in the European Alps. It's a prototype outcrop, and I just thought I'd throw it in here to show you there's a structure here with 2 generations of dikes intruding that structure. There's a chrome dioxide web stripe dike in green, and that's overprinted by this pink and black dike in the middle, which shown on the right-hand side here is this feature, and that's a aluminium augite spinel web stripe dike. So the continental mantle it's very heterogeneous, and it's very, very complex. When we zoom out to the entire globe and look at the depth between 100 and 175 kilometers and in the velocity, and here's all these high velocity regions that we would say need to have a significant Archean component to them. Then we've investigated many areas, and of course we know some areas of Archean are not showing up here because of high heat flow. So Tanzania craton, of course, is also Archean. We know the North China craton is Archean, and also the South China craton has Archean antecedents. However, looking at uranium, lead, and hafnium isotopes of crustal rocks, we're able to see that there are many, many other areas where you're reworking Archean crust. We looked at the Svalbard example before, and also we found similar things from every continent. So in other words, many of these lower velocity regions are also Archean. It's not just the high velocity regions. Then there's the mantle xenoliths. And this is some of our higher quality Archean mantle xenoliths that occur beneath younger terrains. So you can see that we've got them in southern Patagonia, California, southern US, Central Asian orogenic belt, obviously Svalbard, southeastern Australia, and even New Zealand, Archean material in New Zealand. So when you put all that together and systematically map it, we end up with about this much as a summary, as a minimum of the amount of Archean continental mantle. So very quickly you start to realize that, oh, okay, we've probably had pretty much the same amount of continental material for 3 billion years as we've got today. We've just been shuffling the deck of cards by going through 4 supercontinent cycles. And those 4 supercontinent cycles bring all this material together, break it up, bring it together, break it up, etc. And those 4 cycles mean that the crust, the plate tectonic processes, all of the arc magmatism, the rifting, etc., means that the continental crust becomes extremely complex. Many of the original Archean crustal terrains are either destroyed or strongly overprinted, but the Archean mantle roots survive underneath. So we would say that at least 70% of the continental mantle is originally Archean material. And we'll be refining that number for a publication shortly. The One of the key outcomes of this, of course, is that it means that under younger crustal terrains, you've got a lot of old continental mantle. And that old continental mantle is going to have a huge amount of old structure and highly variable composition. So to finish off, I'm going to look at some ore deposit influences, just a few minutes on this. We've got mineral systems at the scale of the entire lithosphere. Here's a plume impacting the thick lithosphere and being channeled by that to the areas of thinner lithosphere where it can decompress and melt. And that's why you end up with the melting focused at things like craton boundaries. And that's why your big nickel deposits are generally associated with craton margins. Over here, you've got this segmented lithosphere, even in arc terrains, will often guide the passage of melts that are responsible for forming many of our large ore deposits. So here's a summarized example from one of our publications showing various nickel deposits of multiple ages around the edges of the superior craton and the nain craton, demonstrating that craton margin relationship. This is a really nice paper integrating multiple data sets, seismic reflection, gravity, mag, geology, passive seismic, as well as magnetotellurics. And this is a fantastic paper by Liu et al. In Geology Reviews this year. And they looked at the patterns. This is on the edge of the North China Craton, just to the southeast, just off the edge of the craton, where the lower Yangtze metallogenic belt is. And they looked at the patterns in the crust here and said, all right, okay, we've got a collision here. We've got some sort of boundary here. There must be a vertical structure here. There's a MOHO offset. And they actually mapped it. And then in the seismic data in plan view, it's actually a low velocity corridor along this trend. And then in the MT cross section, you can see that it's a conductor that's in the mantle coming up into the crust, into that position. And the ore district, which has got the copper gold ore bodies and porphyry and skarn ore bodies, is directly above this position associated with some major structures. So very nice bit of integrated research. And some of you may have seen this. We published this in 2013, but an image of seismic tomography from the US array data from the Western US, where the higher velocity is the red and the yellow and the lower velocities are the blues and the greens. And plotting the bigger deposits and a bit of basic architecture shown here, but not detailed. You can see the Yellowstone hotspot track is very slow velocity because it's hot. But interestingly, the ore deposits are forming at key architectural positions and in areas where the velocity is relatively low, so on the edges of highs. So this is a Paleoproterozoic ore body on the edge of the Wyoming Craton up against the Trans-Hudson orogene. Down here, we've got the Cenozoic Colorado mineral belt, giant deposits, molybdenum deposits and gold deposits, and they are following and intruding along a reactivated Paleoproterozoic structure. And the same for the Jaime's lineament. It's a Paleoproterozoic structure reactivated in the late Cretaceous, and that's where we're focusing some of these Arizona giant porphyry deposits. And then over here in California, there's this low velocity structure here, most likely an old Archean structure, and then second order Proterozoic structures, which are documented Proterozoic structures, have then been re-exploited during the Eocene and host the giant Carlin gold deposits. And of course, Bingham Canyon, copper gold porphyry, is at a triple junction of old cratonic domains. So obviously this is an Archean craton, the Wyoming Craton, but we now also know that this is Archean, both crust and mantle up here. And there are fringing Archean results from the Grouse Creek block but also in addition, we've got abundant Archean, hafnium, isotopic data from granitoids and detritus right across this region. And there's actually some Archean mantle xenolith over here in California. So it's old lithosphere that has a complex, long history. Recently, Hoggard et al. Published a paper showing that the giant zinc deposits in Australia, the big base metal deposits of Northern Australia, hosted by sedimentary basins, are actually localised along the edge of the root of the Australian continent at a depth of 170 kilometres. So it's focusing the sedimentary basins and focusing the resultant ore deposits. And this image of seismic velocity from the Cartbale Craton shows high velocity under the Western Cartbale here. And what we're seeing here is lower velocity under the Bushveld, where you've had some refertilizing melts added to the lithosphere here. But also you can see these linear trends of kimberlites. That's a linear trend. And then this one here is a linear trend. These must be fracture zones in the mantle that then the kimberlites are intruding along and sampling diamonds from the lithospheric mantle. And these in pink are the giant diamond mines around the edges of these high velocity blocks. So fundamental control on those deposits. And it should be noted that kimberlites, if this is a cross section of the mantle, and these are the old depleted zones, and these are ancient structures, and we've got refertilisation along those structures, then kimberlites preferentially come up these old structures. And so they are preferentially sampling the refertilised mantle, and rarely are they sampling the well-preserved, higher velocity harzburgitic material, depleted material. And I'm finishing with, you've got to finish with this image. The fingers of God, the Olympic Dam image showing the old craton margin here on the edge of the Gawler craton, and it's metasomatized, it's conductive, this huge conductor below the crust, triggered by an injection of plume melts, a lot of melting, lower crustal melting, and then a series of giant ore deposits associated with these extensive vertical pipes. So I'll leave it there. This is my conclusions. More than 60% of the continental mantle and continental crust is Archean. Continents are amalgams of cratons and microcontinents, and those microcontinents are ancient, as we saw for the southern US and the Arctic shelf, etc. Tectonothermal reworking is the dominant process affecting the continental mantle and crust. And crustal recycling has dominated over crustal growth since about 3GA. In other words, we've had about the same amount of continent since 3GA. We've just been reworking it and recycling a lot of younger crust. And as we saw, the lithospheric mantle imparts a fundamental control on ore systems. I'll leave it there, Alan. Thanks.
Absolutely brilliant, Graham. It's, you know, as an MT people, we sometimes get stuck in our method, and we lose sight of the fact that our models can be taken by people like you to show implications that are far beyond anything we ever thought of. And it's wonderful to see that MT can be so useful. So while I wait for questions to roll in, I got a couple of questions for you, and that just your very last point about you're rarely sampling harzburgitic mantle. Does that mean that in fact our xenolith database is biased?
Severely biased, absolutely. So the dominant mantle xenoliths that are sampled are leusolite, and that's because when you look back at that image here, they're sampling these structures. They're not sampling the centers of these anomalies. Okay, so when the geochemistry community, mantle geochemistry community, calculated the average composition of the mantle, this is a while ago, 20 years ago, 15 years ago, using what they thought were kimberlites as representative samples, what they came up with was an average sample. The average composition of the continental mantle was lherzolite, and its implied density didn't match the gravity signal, didn't match the geoid. Okay. So Juan Carlos Afonso, who you know well, working with us and realizing through the GLAM project that actually sampling was highly biased, he recalculated, allowing for the fact that you're not getting this representative sampling. And he was able to match the long wavelength gravity signal with a more depleted composition.
We got a couple of questions rolled in. They've come in on the chat rather than the Q&A. The first one is Andy Calvert, who's excuse me, a seismologist. You've sketched the boundaries between the SCLM blocks as subvertical. Could these boundaries have lower dips, e.g. 30, 40 degrees, as implied by some of the seismic reflection data across the Proterozoic Archean collision zone along the western margin of the Slave Craton?
Okay. Look, some of them could be inclined. We do tend to, I guess, see that most of them are steep, but not necessarily vertical, but subvertical. And that's mostly because they're post-collisional. When you get these blocks, and remember, the edges of these blocks become quite soft and warm when they're rifted apart. And so when these blocks reconnect, you tend to sort of squish them up like two cars crashing into each other. And so you end up with a subvertical boundary by virtue of that. But that, I should comment about that Western Slave interpretation, and it probably might get some people upset, but I fundamentally disagree with it. I think that the features imaged are actually fractures and dikes in the mantle and not a paleo-subduction zone, because if that was a Proterozoic paleo-subduction zone, we would have seen the geology of the Slave Craton dramatically altered by the emplacement of that. I mean, we know from Mantle Xenoliths that the Slave Craton has Archean mantle down to 200 kilometers plus, okay? Which would mean that you would be emplacing a huge chunk of Archean under a huge chunk of Archean. The effect on uplift of the crust would be scary to envisage, and you would not expect to preserve low metamorphic grade crustal rocks that are totally undisturbed by that Proterozoic event. So frankly, I think it's a misinterpretation, and that they are actually not, they're dikes. And I mean, I'm happy to argue the toss, but perhaps, but having said that, that's that particular example. There are other examples where there are inclined boundaries in the mantle between mantle blocks. That's pretty clear, I think, from a number of seismic reflection lines, but the inclined, from our observation, as we go deeper into the actual mantle lithosphere, it steepens up. So for instance, there's a good example across the Hardangerfjord shear in southwestern Norway, where you've got a shallow dipping crustal structure. It comes into the continental mantle in the collision zone. It's moderately shallow dipping, but by about 80 kilometers, it's really steepening up. And then it's in the seismic tomography data, and the gravity data, it would appear to be a vertical structure. So, yeah, look, I'm sure it's horses for courses. There would be all sorts of geometries.
Yeah. We know, for example, when you look at Tibet right now, that we have Indian Archean mantle that is being emplaced beneath Asian crust. And so,
do we, Alan? Do we?
Well, I think so. I think the seismic evidence is mapping the.
No. What we've got is an anomaly. Let's start with talking about anomalies. There's conflicting evidence about India being under Asia. So, for instance, we know that the Lhasa block has an Archean basement. Okay. We know the Chengtang block has an Archean basement. The suture zones between them are ancient boundaries that have been reactivated multiple times. I guess to tell you the truth, I paid a lot of attention to the Tibetan Plateau because it's a fascinating area, and I've come away totally unconvinced by models that India is under Asia. In fact, I'm skeptical.
Well, maybe we should set up a discussion on that. But I'll move to some of the other questions. And David Corrigan, it's very nice to see David here. David's a geologist at the GSC. You might know him. Can you expand?
I know David very well.
Yeah. Can you expand a bit on the mechanism of mantle refertilisation?
Okay, so look, any relatively juvenile melt of upper mantle is going to interact with the overlying continental mantle roots and refertilise by adding calcium and iron and aluminium, basically the ingredients of basaltic melts. And when you look over time, what is the most significant agent of this change? So there are two main agents, I guess. One would be mantle plumes impacting the lithosphere through, the last few billion years. But the mantle plumes tend to be point source and relatively infrequent for any given area, whereas subduction is hundreds of millions of years of continuous subduction under many of these terrains. And so when you integrate the flux of magmatism and the fact that it's so aerially extensive right along this margin, then you have a huge amount of melt that is fluxed through the continental mantle. And in addition to the melt, are volatiles. So it's not just water, but it's also, gases, and carbon dioxide, etc. So, I think subduction, our data is telling us that subduction is the main agent of damage to the lithospheric mantle, and regions that have had one post-Archean sort of subduction event or arc event affecting them still preserve quite a depleted root in general. Regions that have had 2 or 3 post-Archean subduction events that cumulatively might be more than 200 or 300 million years of subduction, they really start to show the damage, the effects. They're much more strongly refertilized. And then some zones have had, more than 500 million years of subduction. Some bits of lithosphere have had more than 500 million years of arc activity, arc melts pass through their roots. So they're profoundly modified, and the effect of adding all that material and the water weakens them. So they get weakened from the base upwards. So if we went back to that slide, which, I think I've just screen sharing has stopped. Okay. let me just find the right slide and we'll share again. But okay, one here. Okay, so share that. Oops. Are you seeing the slide now? No, I've got to share again. Share. Okay, you're seeing the section, Alan?
Refertilized the ocean.
Refertilizing Archean roots.
Archean roots, yeah.
So with all the fluids and melt that comes off, remember that the water that's in a slab is mostly lost in this upper 100 to 120 kilometers of vertical subduction. So you really hydrate the base of the lithosphere. I mean, of course, that loss of that water triggers the melting for an arc because it lowers the melting point of the convecting mantle. But basically, all of that water that you're adding, that hydrogen, it's going to help you weaken the base of the lithosphere. So what you find is that the lithosphere that's had huge amounts of subduction under it tends to be thin, relatively thin. So there's a systematic increase in the geotherm. So if you look at Archean terrains, they generally have the lowest geotherms. You go to Proterozoic terrains, they have an intermediate geotherm. You go to Phanerozoic terrains, they have a higher geotherm, simply because the lithosphere is systematically thinned by more and more overprinting. I'm not sure if I've answered Dave's question, but
yeah, well, I think so. Dave, if you want to follow up, just let me know. He says, great answer. So I got a question from Matthew Como, who's an MT specialist. And Matthew's question is a question that every single MT person in the planet wants you to answer. Can you explain some of the causes for the conductive domains in the mantle below those crustal conductive fingers associated with mineral zones?
Yeah. Well, gee. I'm not sure that I should be answering that question, but you know, Alan, if I equated this with anything else that I've worked with regard to geophysical signals, it's always a matrix of effects, isn't it? You know, a combination of chemistry, grain size, and of course that chemistry is not just composition; it's compositional changes, it's, you know, increasing iron, but also then you've got the effects of hydration, micas. There's not going to be a lot of sulfides in the mantle. I mean, there's certainly sulfides in the mantle, but is there enough to make a difference? But maybe when you roll all of these things together, because the most intense metasomatism, you know, it is in areas that do tend to be conductive in the mantle. It's these structures. So you know, I don't know if it's as simple as graphite and not graphite. You know, I don't know. I suspect it's a whole lot of things that must be. Yeah, anyway, look, you guys really need to answer this question for me so that I can interpret my data.
Yeah, but we're mostly physicists, you know. I have been seeing a correlation though with the with these conductive domains in the mantle and the base field.
Sorry, what was that, Alan? The base?
The base of the conductive zone correlating with the graphite diamond stability field. That's what I saw in the slave craton. And we see that in some of the other ones that, in fact, they start at around 80 kilometers and then they stop at around 150, 160, something like that. So this leads me towards a carbon type interpretation.
Right. Well, I'm sure it's a major factor, but like I said, yeah, I guess I would tend to be suspicious that all of these things are a bit of a matrix of combined effects. But I don't know. Look, I'm not the right person to ask this question to, but this is where we need integrated research.
Exactly.
We need to be sponsoring research on experimental work. I mean, I'm not sure what's going on in that area at the moment in MT actually. But I heard that was Kate Selway was doing some, or
I think I don't know. It's my changed. Internet or yours, Graham, but you keep fading out for me. And
yeah, you've frozen on me a couple of times, Alan.
Yeah. It might be my internet. I think I'm freezing, or maybe it's Australia or something. One final question for Andy before you go. Do the seismic tomography models imply Archean CLM exists below oceanic crust, e.g. off west coast of Africa? That's an interesting question, Andy. Thanks for that.
Yeah. Look, that is something we've observed, that it's very common to detach continental crust from continental mantle at passive margins. So this was something that I became sensitized to, I guess, fairly early in the project. And then I discovered a whole lot of petroleum literature about it. And that's now sort of entered the mainstream, a series of publications documenting various margins where sometimes over 100 kilometres, 150 kilometres width of continental crust has been detached from the underlying continental root at a passive margin. So now you eventually, near the margins of that root, you could get, you'll get, well, even depending on the fracturing of the root, you will get some, sills and basalts. But you don't really get proper oceanic crust until you get off that route. At Cape Verde, which is 600 kilometres off the coast of West Africa, the Macquarie group documented definite Archean mantle xenoliths there. So during the Atlantic opening, clearly we're detaching crust from mantle, and some of the mantle is being also broken away from the continent. Some of this old continental mantle is rafting about like a submarine in the Atlantic. And in fact, that fragment, you can map it out with the geophysics. It's I can't remember how big. That's at least a couple of 100 kilometres across from memory. Is the feature that you can map. And there was a publication, O'Reilly et al., 2009, that talked about the impact on some mid-ocean basalts that are interacting with some of this old stuff. I mean, very interestingly, there's, of course, if you're detaching continental crust from continental mantle, that's got certain ramifications. It means that there's bits of continental crust strewn about in the edges of our oceans as well. So, for instance, a ocean drilling program drilled a physiographic anomaly feature 1,500 kilometres southeast of Rio de Janeiro out in the Atlantic, and they drilled into a Neoproterozoic granite. And that's obviously been detached from its underlying root during Atlantic Ocean. Now, of course, the corollary of that is when you close these oceans, you're going to end up with new crust imposed on top of old mantle roots. So this is one of the things that we've had to grapple with in this project, is recognizing when this is the case. So you can actually sample a crustal terrain and find that it's completely young, juvenile terrain, but you've got to be very careful extrapolating that to what is the root underneath, because the root underneath may well be old. So we've certainly found that to be the case. You know, the fact that there's Archean mantle in New Zealand is pretty spectacular, and in Southeast Australia, but both of which are overlain by just what seems to be pretty much Paleozoic crust. Anyway, another long answer, but I think the oceans are a bit more messy than we often assume, due to the effect of continental breakup. Alan, I think you might be slipping offline occasionally, disappearing on me.
Yeah, my internet seems to be a bit flaky this morning. Sorry about that.
That's all right.
Yeah, Andy's saying thanks for a great talk. So thanks again. That was absolutely wonderful, Graham. You've really really shown us what we can do with our MT models, and I'd like to really thank you for your time and showing us the high level information that we can bring to the table. So again, thanks, Graham, and thanks everybody for attending. Merry Christmas, Happy New Year to everyone, and hope to see everyone in the new year. And I'll have this recording up online in a few hours' time. Thanks very much, Graham. Bye, everybody.
Thanks, Alan.
Right.
Good night, everybody. Well, good night for me.
Good night. Yeah, thanks for staying up.